Anyway, leave it. Anyway, leave it. I couldn't figure it out. We leave it. Okay. Anyway, 3D will be good. Okay. So those are the information about the point H, and then we can repeat the same calculation for point K. How about that? Okay. And I will leave the point H here, and then let me erase this part and on the point K. So the same thing, this is a load type, and this is sigma, and this is tau. And for P, the same thing at P, we have the same, the normal stress, and divided by area. And for point K, the same thing due to the normal loading that is compressive. This is 0. The next one, we'll go to V here. We'll go to T, follow up our procedure there. So, and now at this point, you can see using our concept here, the shear stress at point K, let me draw this one here. So now this is our cross section, and our T is in this orientation. The point K is here. So that means that will induce at point H here due to the torsion, the direction of the tau will be in this direction. Right? Okay, so tau equal to Tc over J, and direction like indicated downward. Okay, and now we go to the next one, V, and normal stress is 0, and again VQ over IT. So for this case, let me draw that one here. This is a cross section. This is transverse loading. So will be too quick. Okay, so now we look at here. This is our cross section, and this is transverse loading. So the first we determine the neutral axis, which passes the centroid, normal to the direction of the V. So this is our neutral axis. And now this is point K we want to calculate. So to calculate the shear stress at this point, so basically we make a cut. The cut is parallel to the neutral axis, passing through the point. So this will be our cut.
Oh, Q will be half of the circle.
Yes. So either way, we pick either side. For example, pick this side. Okay, pick this side. Then I need to give you a formula for a half circle. The centroid of the half circle to here, to the bottom here is 3c over 4 pi. So that is the distance from of the centroid of the half circle centroid to the bottom line here. So for this case, Q will be equal to pi over 2r squared. This is the area multiplied 3, if the radius is c, okay. Pi c squared over 2 and 3c 4 pi. So for this case, Q will be equal to 8, 3, 4c over 2 pi. Sorry, 4c over 2 pi. 4c over 3 pi. 4c over 3 pi. So okay, so that will be equal to the c cube 3, 2. Yes, that should be this one. Okay, so for this case, this will be VQ over IT, and here the Q where Q equal to, we calculated 2c cube over 3, and V is given here, and I is pi over 4, c to the 4th power. And what is T? T is the width.
So it's
Oh.
gonna be the.
So 2C. T is the width. And so in this way, using this formula, we are not only calculating the stress at this point, but that value represents the stress at any point along the cut. So basically, this value represents is the average shear stress along this cut, including the point we're interested in. Okay, so here, that is, and what is the direction of the string usually going upward? The same direction of the transverse loading. So from here you can see this string stress due to torsion is opposite to the string stress due to transverse loading. Okay, so down the road, down the bottom here, once we do the superposition, basically the two terms will subtract from each other. So, but anyhow, keep going. So, and now we go to the MY. And this one is 0. And this one for MY, and again, let me draw this one here. So this is a cross section, and this is the Y, and MY is in this direction. This is a point. So for this case, we determine our neutral axis. Neutral axis is about which, for the pure bending, neutral axis is about which the bending applied. So this is the neutral axis. So once we have the neutral axis determined, then the left-hand side is in tension, right-hand side is in compression. So therefore, the point K, and this due to the MY will be tension, and is in tension. The magnitude is MY, and the distance from the point to the neutral axis is our radius, C, and divided by I. I is pi over 4 to the 6 to the 4th power. Are we okay? And now the last one is MZ, the same thing. And this is cross section. This is a Z-axis. MZ, different direction. So MZ basically is like this. So this is the neutral axis about which the bending applies. So this is our neutral axis. And so for this case, the top will be in, yeah, so right away you can tell the point H is here, that is on the neutral axis, so this will be 0. Okay, so basically here that's 0 because due to the M, Z multiply the distance to the neutral axis. So now we can take superposition. So for the superposition, and can I use this space here? So for tau, for sigma, that'll be how many terms? 1, 2, 3, 4, 5 terms, and among the 5 terms, only 2 terms are non-zero. So basically here will be equal to minus P over A and plus My times C pi over 4C to the 4th power. Then again, all the parameters here is only their magnitude because we already take care of the sign here. So this one we calculated, that will be 107.4. And magnitude is in MPa, the positive. And for tau, again, we take the measurements 1, 2, 3, 4, 5. Among the 5 terms, only 2 terms are non-zero. So why not here we give the sign? Say here, say we take the opposite, the positive y direction as our sign for tau. Okay, you can invent any sign you like. Okay, so here if I take the opposite, the going upward, then the TC over J to my sign convention will be negative. Okay, because due to torsion, the second row there, due to torsion, the strain stress is downward.
So that should be a negative one? Over
Negative
there?
1, because here I take my sign convention going up as positive.
Can you put a negative over there?
No,
No?
I already have the direction here. Okay. And then plus VQ over IT. And let me plug in V and Q equal to 2CQ over 3. And I equal to pi over 4 C to the 4th power. T equal to 2C. That's it. And then we do the number. We see that is minus 52.5 MPa. So if I would take the upward positive and then I got the negative value, so basically from here at point K is the strain stress should be downward. So again, let me take up a small cube. For example here, let me pick a small cube. And that cube will be, let me draw that here. Okay. So this is a point K. So I take a very small cube and then I cut into the board and making this one. And basically this surface is our cross section here. And now for this case, we have the normal stress is tension. So on the back, so sigma value equal to 107.4. And then the strain stress is 52.5 at point K is downward. So that means, I need to draw a side here. So on the side, this is the side surface on the back. And in that area, the strain stress is 52 downward. So that means the strain stress on that side is 52 MPa downward. Okay? And again, if on the back of the side, the strain stress is that one, so on the top, the strain stress should be in these directions, and then on the side will be like this, and on the bottom should be go that way. Are we okay? Anyone can follow me? And I've uploaded the homework for this chapter 8 due Friday next week. So, and then we have other 3, and I will try as much as possible today. If I couldn't finish the whole the examples, I believe those notes should be available on Blackboard. Otherwise, I will post the solution on Blackboard. So that is for this question. And then we can try any question before I erase this one. It's kind of complicated, right? Involve a lot of calculations. And the best way is this. Try to leave all the calculation to the very final step, because once you interrupt your thinking by punching calculator, that might give you kind of the connection problem in your brain. That's my experience. So which means once you tabulate all the information, focus on the formula determining the attribute. Okay, and shift your thinking mode from one to another. And then if preferred, then you can summarize using, for example, based upon our cheat sheet. And I think this will be a very good point, and think through what the meaning of every single equation is here. In particular, you can see for this example, when we talk about this formula, we determine the neutral axis. Compared to when we talk about this equation, talk about the neutral axis, they have a different way of the thinking. And again, let me emphasize, this is due to transverse loading. Determining the neutral axis is the way we passing through the centroid, and then the neutral axis is normal to the transverse loading. For the bending, pure bending, the neutral axis is the way above which the bending is applied. Okay, so for everything at this moment, for doing the example or this kind of problem, if you have something not sure how can proceed, then the best way is go back to your lecture notes on that simple either type of the loading, and then go there and think through what meaning of that symbol is. Okay, so that is my suggestion, and then we can go to the second one.